So, hello everyone again in this second series of talks. We have the second talk about stable and singular equivalences of finite dimensional algebras by Georgios Dalezios. So, George, you can start.
Thank you very much. Thank you again for the invitation to speak in this seminar. So this will be part 2, and we will be talking about the stable and singular equivalences of finite dimensional algebras. So I would like to recall a few things we did last time in the last talk. So last time we talked a lot about equivalences between categories of modules or module categories, and how these were generalized to equivalences of derived categories of rings. Let me just recall you in a sketchy way about the categories we considered last time. So we had this mod A here is the category of all modules over a ring. And by C of that, I mean chain complexes that we defined last time. Then one passes to the homotopy category of all modules, which is denoted by K of mod A. And then you can further go to the derived category of the module category. So this is the notation about all these categories. And the point last time was that we discussed Morita theorems, which means equivalences of such things. And we focused on equivalences between module categories for two rings A and B, and about the more general theory of equivalences of derived categories of rings. So let me just recall you that the derived category of a ring is that you take the homotopy category and you invert all the quasi-isomorphisms. So you create a new category where any morphism of chain complexes that induces an isomorphism in homology becomes an isomorphism now in this derived category. And a clarification from last time is about derived equivalences. And I want to say that for any ring, you have the following things being equivalent. Part 1 tells you that the full derived categories of the ring, where this capital mod A is that you take all modules over your ring, not necessarily finitely generated modules. If you have D of mod A equivalent to D mod B, of course, all these have to be equivalences of triangulated categories. Let me recall you that already at the level of the homotopy category of complexes, you have a triangulated structure that we briefly explained last time, and the same is inherited for the derived category. So any triangulated equivalences between D mod A and D mod B is equivalently given by a triangulated equivalence between this KB of prods A and KB of prods B, where by KB I just mean bounded complexes. So there are zeros left and right for these complexes, and degree-wise they consist of finitely generated and projective modules. And in fact, this is equivalent to having a triangulated equivalence between dB of small mod A and dB of small mod B. Here the B means bounded up to homology. I will explain this in a bit. And the small mod here means that you take finitely presented modules, so finitely generated if your ring is Noetherian, for instance. And let me briefly recall these definitions again here. So this KB of prods A has object complex of this form. Here, left and right, I have zeros. And what is inside is just finitely generated and projective modules. And last time I talked about a class of complexes that are called perfect. And I told you that these are complexes that are isomorphic in the derived category of the ring to complexes that are of this form above here. And actually, as subcategories of the derived category, you can identify these classes of complexes. So you can think of either class here. I advise you for this talk to think of this KB prods here because it's more directly explained here. So the other thing that appeared in the previous slide, the DB, this has objects, certain complexes that are degree-wise, they consist of finitely generated modules, but here the B means that they are of bounded homology. So the homology of the complex is bounded. Maybe your complex is not bounded, but its homology has to be bounded. And of course, you can see that there is an embedding of categories here. So here I have KB prods, and this, of course, is a subcategory of this DB mod A. So these bounded complexes, of course, are homologically bounded. And you have this inclusion here. Now, why is this interesting for us here? Let me recall from last time, near the end, I explained some famous result on homological methods by Sarah Auslander and Buxbaum from the 50s. So this tells you that whenever you have a commutative local Noetherian ring, the following things are equivalent. The first is that the ring is regular in the sense that the Krull dimension of the ring equals the dimension of your maximal ideal modulo the maximal ideal squared over the residue field of the local ring, which has a geometric meaning, as we briefly said last time. Now, the other two conditions are homological. The second tells you that all modules have finite projective dimension. And the third is the same condition with finitely generated modules. And the projective dimension of the module, I should explain to you that last time we saw the process of taking a free or a projective resolution of a module. If this stops, in the sense that if the complex you create has zeros after some point, then you say your module has finite projective dimension. So this is a homological characterization of something geometric, which is interesting. And observe that in this type of rings here, because of this result, as I told you, every module has finite projective dimension, so you in fact get an equality between these two categories here. As I told you, this homotopy category of projectives is always embedded as a subcategory here, but in this case, you have an equality. So this derived category somehow reduces just to having a bounded homotopy category of projectives. And having in mind this result, we can think in general that this KB prods of some ring is somehow its smooth or regular piece, if you want. Take this as a general philosophy. And this takes us to the definition of the singularity category of a left Noetherian ring. And this is just this quotient. I mean, you have the quotient of the bounded derived category of mod A modulo this subcategory of bounded complex of projectives. And of course, by the previous result, if your ring is regular and local, this happens if and only if the singularity category is zero. So, and this is where the terminology comes from in general. And in this talk, we want to understand the equivalences between singularity categories of certain rings. In general, this is not an easy question or a question that can be tackled for many classes of rings simultaneously. So there are different theories for if you think of commutative rings or finite dimensional algebras. And in these talks, we will say something about finite dimensional algebras, but we will also review a few standard things about or classic things about commutative rings and singular equivalences between them. So I should tell you right away that before this definition as I explain this definition comes from Buchweitz around the 80s, but before that, the stable module category of a group ring was well studied, and it was a more classic topic than the singularity category. And the stable module category of an algebra in general is defined as follows. So you take, here I have the finitely presented module. So you take objects to be the same as small mod A, so just finitely generated modules, and the morphisms between two modules in here, they are described by this formula. Here I have all homomorphisms of m comma n in this new category to be given by a quotient of all homomorphisms in the initial category, where I have divided by an equivalence relation. And the relations tells you that two maps F and G that have the same source and target, they are identified here if they are difference factors to a projective module. So in a picture, you can think of this like this. And in particular, the projective modules themselves will be killed in this homotopy category, because the identity map of a projective and zero will be equivalent, will be in the same equivalence class. So the projectives will be zero in this category. Informally, you can think of this as some kind of quotient of categories here, that you have this small mod A and you have killed with the projectives. And there is something important about certain stable categories for certain rings, namely they have a structure of the triangulated category. So let me briefly give you this structure. In general, for any module, you can surject from some projective and you can take the kernel. And this assignment of taking m to omega m, this can become it's not a functor in general, but it can become a functor at the level of the stable category. It can become a functor with big M here without the finitely presented, but over a Noetherian algebra, it is also a functor between the small mod A, stable category of this. And it is a classic result here by, actually, it's a special case of a result of Happel, that if you have the group algebra of a finite group, then the stable module category is triangulated, and the automorphism on this triangulated category is given by this CZG functor. And this is crucial for employing methods of triangulated categories to group representations and has been used a lot. We're not supposed to understand the triangulated structure of this category in this talk, but this is an important fact that has led to many developments. So I stated here. Now, about the relation of this and the singularity category we talked before, note that there is always a commutative diagram here, like this small mod A, of course, can be embedded into the bounded derived category, and then you go to the quotient, but then the projectives will, of course, be, they of course limit this category here, this KB of prod, so there is an induced functor. And the result here, which is a special case of a result of Ricard, is that if KG is the group algebra of the finite group, then this functor F is an equivalence of categories. So in this case, this singular category, the singularity category, agrees with the stable module category, which is something classic. But in this talk, we don't want to consider group algebras, but more general classes of finite dimensional algebras. And in general, this stable module category will not be the same as the singularity category. I mean, you have a functor, but it might not be an equivalency if you consider larger classes of algebras than group algebras. So let's talk about these larger classes of algebras now. here we have an hierarchy, let's say, of finite dimensional algebras. So I start with a semi-simple that from a homological perspective don't say anything interesting. Then this can be embedded to something called symmetric. I will explain to you the definitions in a bit. These are all symmetric, and then symmetric can be embedded to what is called Frobenius. Frobenius is always self-injective, and then the Gorenstein is a generalization of self-injective algebras. So what about the definition here? Symmetric means that you have an isomorphism between your algebra and the dual of your algebra. So all these are finite dimensional over some field K, and you want this to be an isomorphism as bimodules. Now, Frobenius occurs as a relaxation of the above concept, where you want this isomorphism to restrict it to left modules only. And self-injective, as you can see from the phrasing, means that your algebra is injective as a left module over itself. Now, Gorenstein is a generalization of self-injective in the sense that you want your algebra to have finite injective dimension over itself as a left module, but here you also include that you want to have this as a right module. And self-injective and Frobenius are left-right symmetric concepts in the sense that I could have given you here the definition of Frobenius or self-injective via right modules instead of left modules, but this will be equivalent. For Gorenstein, this we don't know. We don't know if these conditions are independent or not, so we state them both. Let's see some examples of these classes of rings. So for symmetric, there are some classic examples here. The matrix algebra is symmetric, and you can set up an isomorphism of bimodules by your algebra to the dual of your algebra by considering the trace map in this way. Here, it's important that the trace has this property that the trace of a product of two matrices m times n is the same as the trace of n times m. So this is important to construct an isomorphism of AA by module here. Now, another classic example is that of a group algebra of a finite group over a field. So here you have a K-linear map where each element of your group, for each element of your group, you pick the lambda corresponding to the identity element of your group. And then you can set up an isomorphism of AA by modules via this map in a similar style as we did with the trace above. So this makes the group algebra a symmetric algebra. And some other classes of examples I should give you. One is here about self-injective algebras, is that any quotient of a PID by an ideal. Note that this is not, here I'm not talking necessarily about finite dimensional algebras, but the definition can work for Noetherian algebras more general. So any quotient of a PID by an ideal will be self-injective in this more general sense. And for a more combinatorial example here, you can take a quiver with two vertices and two arrows like this, and consider the ideal where you kill alpha beta and also beta alpha, so you create some kind of symmetric situation here. And if you take this quotient of this path algebra modulo this ideal, this will give you a self-injective algebra. Now, for Gorenstein, obviously you have that all self-injective algebras are Gorenstein. And also all algebras of finite global dimension will be Gorenstein. So finite global dimension means that if you run the projective dimensions for all modules in the ring, you need the supremum of this to be finite. Here I should have said, yeah, this is the definition of the global dimension. And if this is finite, you say your algebra has finite global dimension. So all these will be Gorenstein. There are examples, of course, that are not self-injective and not of finite global dimension. Here you can see in a combinatorial style again how you can create one, given by this quiver and relations. And there are other constructions you can do as well. You can take any self-injective algebra and then construct this triangular algebra given by these blocks, and this is Gorenstein. So there are many, many examples of algebras that are Gorenstein. If we think of the singularity category, this part 2 here might not be very interesting, because for any algebra of finite global dimension, the singularity category will be 0, but for the rest, we get something interesting in terms of singularity categories. Now, I should tell you that more generally, this was about finite dimensional algebras, but more generally, there is the definition of a Ivanaga-Gorenstein ring, which is a ring which is two-sided Noetherian, and the injected dimension of the ring, left and right, is finite. Of course, for a finite dimensional algebra, you do have that it's two-sided Noetherian, so this is a generalization of the previous concept. And it is quite important because it includes some examples coming from commutative algebra. For instance, if you take the power series ring in n variables, say over the complex numbers, and you mod out by some polynomial, you create a ring which will be Ivanaga-Gorenstein in this more general sense. And the keyword here is to look up for complete intersections in commutative algebra. This will be Gorenstein. Ivanaga-Gorenstein. So what about these Gorenstein rings? What is special about them? There are some results that are interesting, and one of them comes from Eisenbach in the 80s. It says that if you start by any regular local commutative Noetherian and you kill by some element f, so an example of a complete intersection here again, then there is something interesting that happens here. So any minimal free resolution for any module, for any finitely generated module over this quotient, this will become periodic with period 2 after finitely many steps. So this phenomenon means that the periodicity here means that after some point in the projective resolution, the projective resolution will start to look like this. You have QP, 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 and this gets repeated all the time. So in particular here, note that if you take the kernel of any of these maps, you get a module which admits a resolution by projectives, but now this goes in the wrong direction. So intuitively, you have in mind that the projective resolution of your module goes to the left, say, by construction, but here you have this phenomenon that gives you also some kind of resolution by projectives in the wrong direction. But this creates some interesting class of modules here. And these will be the modules that are called Cohen-Macaulay or maximal Cohen-Macaulay modules. So over Gorenstein algebra, a finitely generated module is called Cohen-Macaulay or maximal Cohen-Macaulay, depending on terminology, if it will be a CGG, it will be a kernel in such a complex as we had before. So you have an acyclic complex of finitely generated and projective modules, and your module is a kernel somewhere there. This class of modules will be denoted CM of A in this talk. And pictorially is what I described to you before. So you have your module here on the left, you have an acyclic complex of projectives, which resembles your projective resolution. But here on the right, you also have some resolution by projectives again. and all these P's are cyclic, and Z is a kernel here. So Z will be a Cohen-Macaulay module in this case. This is a special class of modules with many interesting properties. So let's see some remarks about these modules first. So any projective module will be Cohen-Macaulay for the trivial reason. You can take this complex here. It is acyclic. It consists of finitely generated projective modules. So small p stands for finitely generated projectives. And this appears as a kernel here, P. So any projective module is Cohen-Macaulay for a trivial reason. So the interesting class of Cohen-Macaulay modules, say, will be that they are not projective Cohen-Macaulay modules. Now, as another nice remark, observe that over a self-injective algebra, any finitely generated module will be Cohen-Macaulay. The reason for this is that over a self-injective algebra, the injective and the projective modules coincide. So you can take any module. On the left, you have your projective resolution. On the right, you have your injective resolution. But again, this will be a resolution by projectives in the wrong direction because injectives and projectives coincide in this class of algebras. So you glue these two together and you take a complex of projectives, which is acyclic, and your module is a kernel in that. So you get that any module is Cohen-Macaulay over a self-injective algebra. And it's kind of a typical strategy to try to extend results from self-injective algebras to Cohen-Macaulay modules over Gorenstein algebras. So the Gorenstein algebras is a more general class than the self-injective. In the self-injective case, the Cohen-Macaulay modules are just all modules, but in the Gorenstein case, you have Cohen-Macaulay modules that are not trivial. So it's interesting to extend results from self-injective to Cohen-Macaulay over Gorenstein algebras. And I should tell you that this concept of Cohen-Macaulay modules has been generalized to any ring. So I gave you the definition over Gorenstein algebra, but over an arbitrary ring, this definition has been extended to the concept of Gorenstein projective module. These will be some modules that they will satisfy the condition I gave you for the Cohen-Macaulay over Gorenstein, but you also want them to satisfy some extra condition, which is automatically satisfied for Gorenstein. But we will not say much about this class of modules in this talk. Let's see some examples of Cohen-Macaulay modules. So over this ring, for instance, you can create an acyclic complex of projective modules just by taking multiplication by x. Here, the kernel of this map is again generated by x, modulo x squared, which is the maximal ideal of your ring. So you create, so K will appear in particular as a modulo of this kernel. So you create an acyclic complex of projectives where if you take the CSG anywhere, if you take the kernel anywhere, you take just K. So K is an example of Cohen-Macaulay module by this resolution here. Here, this is the other combinatorial example of self-injective algebra I gave you before. So you have two arrows, two vertices, and this symmetric situation here, and your algebra decomposes as a direct sum of these, of what is generated by the constant paths here, E1 and E2. And you can form two short exact sequences here. From P2, say you can subject to the simple module supported at the vertex Q. This you can always do, and the kernel will be the radical of this module. But in this case, you can compute that the kernel is given by the simple module supported at the vertex 1. And because the situation is symmetric, you have exactly the same if you interchange 1 and 2 here. So you create these sort of exact sequences, and if you glue them together, you get an acyclic complex of projective modules. And this S1 and S2, they are Cohen-Macaulay modules, and they are not projective. So of course, you could tell this because I told you that this algebra here is self-injective, but here we construct the resolutions. So to construct the resolution is something of extra interest, let's say, than just knowing that something is Cohen-Macaulay. So I hope now you have many examples about this. Now, let's pass to what is known as the stable category of Cohen-Macaulay modules. So as I told you, the projectives are inside the Cohen-Macaulay modules, and you can take the stable category, which is again defined in a similar style as the stable category of a finite of a group ring, as I gave it before. So here again, the objects in this category will be the Cohen-Macaulay modules, and two morphisms will be identified if their difference factor to a projective. So it's the same definition basically. And again, by applying this result of Happel, you have that over a Iwanaga-Gorenstein ring, so Gorenstein in the general sense, commutative and non-commutative if you want. Then this stable category will be triangulated with automorphism given again by this omega exactly as I gave it before. Now, this result of Happel works for group rings and for this case. And in fact, what Happel has done is that he has defined some kind of additive categories that are called Frobenius. And the main property in these categories is that the projectives and the injectives inside, so taken in a relative sense, inside these Frobenius categories, they coincide. And for such categories, he has a general result that the stable categories of such categories, they are always triangulated. This is why you get this special case here for the Cohen-Macaulay modules, and you also have a special case for the group algebra of a finite group, or for a self-injective algebra more generally. Now, how does this relate to the singularity category? For Gorenstein, you have that the canonical factor that you get from the Cohen-Macaulay modules to the singularity category, which factors through the stable category of Cohen-Macaulay modules, is an equivalence of triangulated categories. So this is the analogous thing, or like the more general thing that I told you before about stable module categories or self-injective algebras more general. And the result in this case is attributed to Ricard, but this result of Book-Weitz appeared earlier than Ricard, so I will assume they are independently obtained. And just a comment here, I should tell you that Book-Weitz passed away in 2017, and he proved this result up here in a manuscript which is unpublished. It's called this Maximal Cohen-Macaulay modules and things. This is a very famous manuscript. It stayed unpublished for some reason. It has been cited more than 500 times by Google search, and sure it's much more, but just Google detected this number. And this has now appeared as an AMS publication, has been curated by many interesting people who work in this area. So now I gave you some nice examples of singular equivalences. I told you what are these. Sorry, for singularity categories, I told you what are these for the Gorenstein algebras. They're given by stable categories of Cohen-Macaulay modules. So you now have some information about the categories, and I want to pass to look at the equivalences between such categories. Now, the problem here is that there is no Morita theory for stable categories or singularity categories. So let's look at an example again. If you have these two rings that have appeared before in these talks, if you have these two rings, and then by looking at the indecomposables and modulo the projective modules, you can set up an equivalence of additive categories here. So this kx mod x squared will have two indecomposables. The one is the ring itself, the other is k. You kill the ring itself because it's projective, so you just stay with k. And here, if you kill the projectives, you will only stay with the second column here, which is again isomorphic to k. So modulo projectives, these categories really come from just a vector space. And you get an equivalence of additive categories. The problem, so here it's just a fact that stable equivalence preserve a number of indecomposable in general, but this is a fact that it's not very useful to construct any Morita theory, because you do not know if these equivalences are given by any reasonable functor as a tensor product of bimodules or anything like that. Recall that this was the case for the Morita for Morita equivalences, but here these equivalences look a bit random. You don't know how they appear. They just appear like this. So there is, to remedy this fact, we will give an extra definition of a special case about these equivalences. Before this, I will need to remind you of Morita's theorem once again. So recall that Morita's theorem discusses equivalences between module categories given by module and two functors like this. And in fact, this other functor here, this home, you can prove that this is also given by a tensor product. So both functors are given by tensor products. So the reformulation I want to give you is that two rings are equivalent. Sorry, the module categories of two rings are equivalent if and only if you can find some bimodules which are finitely generated and projective when restricted on each side, such that you have some isomorphism here when you tensor these two. So, and tensor M will give you an isomorphism of bimodules like this, and M tensor N will be isomorphic to B as BB bimodule. So take this as a reformulation of Morita's theorem. So Brouet has taken this reformulation, let's say, and put it in the context of stable equivalences. As I told you, this can be a bit random, so he defines some nice situation of a stable equivalence here, which is given by bimodules. So say you have two bimodules over finite dimensional algebras that are finitely generated and projective on each side, and say that you have a situation like this. Here, if you tensor them, you get an isomorphism like this, A plus P. P here will be some projective bimodule. This A to the E here is the enveloping algebra, is a way to express that something is a bimodule. So P will be a projective bimodule here. And the other equivalence tells you that M tensor N is isomorphic to B plus Q. So it's kind of the mirror situation of one, where Q is again a projective bimodule. In this case, you say that this pair M comma N defines a stable equivalence of Morita type between A and B. And in this case, the functor, if you tensor with M, you do get an equivalence between the stable categories with inverse the tensor with the other module. So in this case, you do get a stable equivalence, but it comes from a nice functor, a nice situation. that's how you remedy the fact that you had these random stable equivalences in the previous slides. And because these are given by tensors, they have some nice properties. You can prove that they are invariant. Some concepts stay invariant here, stay under a stable equivalence of Morita type. So if under mild assumptions, probably if you have a symmetric algebra and a stable equivalence of Morita type, the other algebra will be symmetric. And Hochschild homology and cohomology groups in positive degrees will be isomorphic under a stable equivalence of Morita type. There is a conjecture here that the number of simples is preserved under a stable equivalence of Morita type, at least under the extra hypothesis of having an algebraically closed field. This is known as the Slender-Wrighton conjecture, and this is equivalent to asking that this group here, HH, Hochschild homology at the zero level, stays invariant under a stable equivalence of Morita type. And this group is given by something classic, so it's your algebra modulo the commutators of your algebra. So we see that at least here there is an open problem related to this stable equivalence of Morita type. So you don't get anything for free under this concept. There are questions that might be very difficult. Now, this concept has been generalized recently to accommodate equivalences between singularity categories that are given by nice tensor products. So the situation here is again that you have two bimodules, finitely generated and projective. And here what he has done is that he changed the situation from the previous definition of Brouet by shifting this regular module here to some high CZG in the resolution of this as a bimodule. So this is a small twist in the definition of Brouet. And when this happens, you say you do have a singular equivalence of Morita type with level n. N is this natural number that appears here. And it is the case that in this situation, you do get a singular equivalence given by tensor products. So you have a nice singular equivalence. And for n equals 0, you obtain exactly the definition of Brouet I gave you before. So this is a nice generalization of Brouet's definition to accommodate singular equivalences. And here you can also prove that these have some nice properties. So Gorenstein's of algebras is preserved, for instance. There is a comment in the chat here. Does n have to be the same in 1 and 2? Yes, it has to be the same, yes. So these also have nice properties. And now let's focus on a theorem of Ricard on stable equivalences. It tells you that whenever you have finite dimensional self-injective algebras, so think of group rings if you want, over an algebraically closed field, then any stable equivalence which is induced by an exact functor, it will be of Morita type. So when I say induced by an exact functor, I mean that we have this situation here. We have some exact f, and this reduces down to a stable equivalence, to an equivalence between the stable categories here. But here he has cheated a bit because this exact functor here at the level of module categories by classic result of Watts means that your f is given by tensoring with a bimodule. The bimodule here will have to be projective on both sides for this functor f to be well defined at the level of stable categories. So he starts with one bimodule, and he tells you that if the tensor with this gives you a stable equivalence here, then this is nice. So then you can define some other bimodule such that the pair satisfies all this weird definition of Brouet that we saw earlier. Now, my question is if we can generalize these results to Gorenstein algebras and to Cohen-Macaulay modules, because this is a result of self-injective algebras. I want to lift it to Gorenstein. So the approach here is to take the analogous thing somehow, but in a more general style. So you have here Gorenstein algebras, you have a functor induced by tensoring with a complex of bimodules. This has to have some properties in order to have a well-defined functor between the singularity categories, and the property is that this X, when you restrict it on both sides, it has to be a perfect complex. And the result I have about this is that for Gorenstein algebras, again over an algebraic closed field for technical reasons, and for this situation where you have a complex X inducing a singular equivalence like this, there is an induced singular equivalence of Morita type with level. So here you start with something which is relatively abstract, so an equivalence given by just tensoring with a nice complex of bimodules, and you construct two bimodules with all these properties that appear in the definition of singular equivalence of Morita type. And this can happen over a Gorenstein algebra. So how to connect this to the Cohen-Macaulay modules over Gorenstein algebra? Here, the analogous thing is to consider an equivalence between stable categories of Cohen-Macaulay modules given by a tensor product with a bimodule. Here, the bimodule has to have these properties in order for this to be well defined. And if you start with such a thing, then you can find some other bimodule n such that this pair defines a nice singular equivalence, so a singular equivalence that satisfies all the properties that appear in the definition I gave you before. And here, the level n will be the projected dimension of this. This will be n actually, the projected dimension of this module here. Now, if you have a self-injective algebra, this n will be 0, and all Cohen-Macaulay modules are just like they agree with the category of all modules. So you do recover Ricard's theorem for self-injective algebras. So the above is a straightforward generalization of Ricard's theorem. In the last few minutes, I would like to explain some other result which starts from this question, that how can we find or construct these stable equivalences of Morita type, or the singular equivalence of Morita type? So they are nice equivalences. They have many consequences, but how can I know, is there a machinery to construct many of them? We will discuss an approach here which is based on what is called an Auslander algebra. Here is a quick reminder that over a finite dimensional algebra, you do have a Krull-Schmidt result. So any finitely generated module can be decomposed as a direct sum of finitely generated and decomposable modules in an essentially unique way. And the definition here is that your algebra is of finite representation type if there is only a finite number of isoclasses of decomposables. Now, the Auslander algebra of an algebra of finite representation type is defined as follows. Say you have n indecomposables up to isomorphism, so your algebra is of finite representation type, and you take the direct sum of these. And you take the endomorphism algebra of this module that occurs. This is the Auslander algebra, by definition. For example, you can play a bit with all these algebras we had before. Say this algebra of dual numbers, this is of finite type. I told you you have two indecomposables here, your algebra itself and K. This will correspond to the two vertices here in the Auslander algebra. And if you study the maps between them, you can express this Auslander algebra as a quiver with relations. You can take this as an example. And now about the construction of nice stable equivalences, take two finite dimensional algebras A and B, and I will denote A tilde B if there's a stable equivalence of Morita type between them. And the result here is by Liu C, and tells you that if you start with representation finite dimensional algebras, and you have a stable equivalence of Morita type between them, then this will pass to the Auslander algebras. I should make a comment that this is not true for stable equivalences that are not nice, that are not of Morita type. So if you take this example with the random stable equivalence I gave you before, and you compute the Auslander algebras of these two things, you can find a numerical invariant that breaks here. So the numerical invariant is what I briefly said earlier, is that under any stable equivalence, the number of non-projective indecomposables will be preserved. This is not preserved here. So this result of Liu C holds for stable equivalence of Morita type. For random stable equivalences, it might break. Now, my concern here is to find a version about this result of Liu C about Gorenstein algebras and Cohen-Macaulay modules. So to take this direction, let me briefly tell you that I will work now for this concept of Gorenstein projectives that I told you that it generalizes the Cohen-Macaulay modules over Gorenstein. You can stick with Cohen-Macaulay modules if you want over Gorenstein algebras. This is not a problem. The definition here is that an algebra is of finite Cohen-Macaulay type if there is only a finite number of isomorphism classes of indecomposable, finally generated Gorenstein projective modules or Cohen-Macaulay modules, if you want. So this is kind of the relevant relative concept of representation finiteness with respect to this class of Cohen-Macaulay modules. Of course, over self-injective algebras, the two concepts will be the same, but in general, we have this concept of finite Cohen-Macaulay type here. And again, here you have many, many examples of such things. There is a very nice paper here by Zhenzhen and Su that gives you a combinatorial way to construct algebras of finite Cohen-Macaulay type, starting by any monomial algebra. So in this talk, a monomial algebra will be some finite dimensional quotient like this, and I will be generated by monomial relations, okay, where the paths are taken of length greater than 1. So you have many examples of these things. The definition is not empty. Now, the analogous definition of Auslander algebra I gave you before about representation finite algebras here is lifted by Beligiannis to this relative situation when you have an algebra of finite Cohen-Macaulay type, and you assume that x1 up to xn up to iso are all the decomposable Gorenstein projective modules you have, and you take the direct sum of this and the endomorphism ring of that, and this is called the Cohen-Macaulay Auslander algebra of A. And Beligiannis has proved here that this algebra has finite global dimension if and only if A is Gorenstein. So in the non-Gorenstein cases will be quite different than the classic Auslander algebras that are known to always have finite global dimension bounded by 2. So now I want an analog of this result of Liu C I told you for Gorenstein algebras of finite Cohen-Macaulay type, and for algebras of Cohen-Macaulay type more generally, even if they are not Gorenstein. So I will write this ugly notation CM Auslander of alpha for the Cohen-Macaulay Auslander algebra of a semi-finite algebra. This is just for this talk. It's not a standard notation. So the result here which has not appeared on the archive yet, tells you that if you have two finite dimensional Gorenstein algebras of finite Cohen-Macaulay type, then if you have a stable equivalence of Morita type between them, there is an induced stable equivalence of Morita type between these Cohen-Macaulay Auslander algebras. And what can you say about the non-Gorenstein cases? About the non-Gorenstein cases, you need to restrict a bit the type of stable equivalence of Morita type that you consider. And this I write as a nice stable equivalence of Morita type, and I will tell you in a bit what this means precisely. So I write A double tilde B if there is like a very nice stable equivalence of Morita type. And here the result tells you that if there is such a thing between two algebras that are of finite Cohen-Macaulay type, but they might not be Gorenstein now, then you get again a stable equivalence of Morita type with this extra nice property for the corresponding Cohen-Macaulay Auslander algebras. And we also have some analogous results for singular equivalences of Morita type, but let's not talk about this now. So what is this very nice stable equivalence of Morita type that you have here? There is a definition that has been given by Xi. It tells you that if you have a stable equivalence of Morita type given by a pair of bimodules, then you call this of adjoint type if these functors here are adjoint pairs. So you want M tensor M to be left adjoint to M tensor blank, but you also want the opposite. You want M tensor A to be right adjoint to this. I think this is called Frobenius adjunction or something like that. So this is like an extra property you want imposed on your stable equivalence of Morita type. This seems a bit restrictive as a concept, but the point is that it is not very restrictive, because there is a result here that tells you that if you start with an ordinary stable equivalence of Morita type, induced by a pair of bimodules, then under mild assumptions, this can give rise to a stable equivalence of adjoint type. The mild assumption is that your field has to be algebraically closed, and one of the algebras has to be indecomposable as an algebra. So not really very restrictive assumptions here. So our result that tells you that if you start with a stable equivalence of adjoint type between algebras of finite Cohen-Macaulay type, and you pass to this stable equivalence between the Cohen-Macaulay Auslander algebras, this result actually uses mild assumptions on the algebras. And it's true for algebras that are not even Gorenstein, just finite Cohen-Macaulay type. So I will finish with this result. And thank you for your attention.
Thank you, George, for the very nice talk. Let me stop the recording.